Good day everyone. In this video discussion, I will discuss a types of function, namely the exponential and logarithmic function. These functions have application in variety fields including science, engineering, and business, to name a few. In fact, these functions can be found in almost any fields that employs rudimentary level of mathematics. We may have encountered various types of functions in mathematics, such as polynomial functions, even odd functions, rational functions, and trigonometric functions, among others. However, once you get past the notation and start to understand some of the properties, you will find that it is easy to understand. Introduction. A function is a binary relation between two sets in which each element of the first set corresponds to exactly one element of the second set. But before discussing the logarithmic and exponential function, let us first review the basic laws of exponents, such as a raised to 1 equals a, the value of a and b raised to n equals a raised to n, and b raised to n, and so on. You can see in the presentation the different examples of the laws of exponent. Example number 3 states that the value of negative 8 raised to 5 over 3 is equals to cube root of negative 8 raised to 5 is equals to 2 raised to 5 is equal to negative 2 times 2 times 2 times 2 is equal to 32. However, negative 8 raised to 5 over 2 is undefined. Knowing the exponent rules, we can evaluate a large number of expressions without using our calculator. Consider the following scenario we have encountered first in the presentation. So, if we attempt negative 8 raised to 5 halves, we can have a problem because negative 8 raised to 5 halves is equal to square root of negative 8 raised to 5, and a square root of negative 8 is undefined, or at least it is not a real number. We simply say that the value of negative 8 raised to 5 halves is not defined in this case. Exponential function. An exponential function is a mathematical function in forms of y equals f, then the value of x equals b raised to x, where x is a variable and b is a constant, which is called the base of the function, such as b is greater than 1. Exponential function. An exponential function is a mathematical function in forms of y equals f, then the value of x equals b raised to x, where x is a variable and b is a constant, which is called the base of the function, such as b is greater than 1. For example, f times x is equals to 1.7 raised to x, or y equals 1.7 raised to x. Another example is f in terms of x equals 2x, f in terms of x equals 3x, f in terms of x equals 12x are exponential functions. Graphs determine domain, range, function, 1, and negative 1, x-intercepts, y-intercepts, asymptotes. F in terms of x is equal to 2 raised to x. Graphs determine domain, range, functions, 1, negative 1, x-intercepts, y-intercepts, asymptotes, such as g in terms of x is equal to the value of 1/2 raised to x. Growth and decay, f in terms of x is equal to b raised to x, where growth if b is greater than 1, and decay if 0 is less than b and is less than 1. Next is properties of graphs of exponential functions. Number 1, functions and 1 to 1. Y-intercepts is 0 and 1 and no x-intercepts. Domain is all real numbers. Range is y such that y is greater than 0. Graph approaches but does not touch x-axis, or x-axis is asymptote. Growth or decay determined by base. Natural base E. E s is x, to infinity times 1 plus 1 over x raised to x is equals to e, such that the value of e is approximately 2.718281828. In computing the exponential function, we should use a scientific calculator. Calculator case includes second function of divide, second function of ln or left side e raised to x. If we let a equals 1 and f in terms of x, as a x, we get f in terms of x equals 1x equals 1, which is in fact a linear function. So let's graph the exponential function f in terms of x equals 2x by substituting the value of x to get the value of y. So as you can see in the graph, we agree that the exponential function base is never number 1. To recap, an exponential function has form f in terms of x equals ax, where an is a positive integer is a non-zero positive constant, because in the example, a raised to x may not be defined if it is a negative we acquire to be a positive. So by looking at the graph, it's worth nothing that any x, f in terms of x, is equal to 2x is a positive. However, as x moves, it gets closer to 0 in the inverse direction. However, because 2x is greater than 0, the graph never touches the y-axis for any x to x axis. The function f in terms of x equals 2x grows very rapidly as x moves in a positive direction. Because f in terms of x is equals to 2x is defined for all real numbers, the domain of f in terms of x is R. The graph suggests that the range is all positive real numbers, and that is the range is the interval of 0 and 1. Let's look at the exponential function f in terms of x equals 1 raised to x over 2 and compare it to the first graph. So, by looking at the graph, unlikely y equals 2 raised to x, this function decreases as x increases. In fact, f in terms of x is equals to 1/2 raised to x equals 1x over 2x equals 1/2 raised to x. As x increases towards infinity, the denominator 2x becomes even bigger, so the fraction f in terms of x equals 1 over 2 raised to x gets closer and closer to 0. But no matter how big x gets, we still have f in terms of x is equal to 1/2 raised to x is greater than 0. Some exponential functions. Each exponential functions f in terms of x equals ax has y-intercept f in terms of 0 equals a raised to 0 equals 1. If a is greater than 1, then f in terms of x equals a raised to x increases as x increases. If 0 is less than a and is less than 1, then f in terms of x is equals to a, x decreases. So after discussing the basic rules of exponential function, let us move on to the application of simple interest, where a equals amount, p equals principal, t equals time, and r equals rate, with the formula a equals p plus p r t. Sample problem for simple interest. For example, if an account earns 6% compounded quarterly, and the amount at the beginning of the first quarter is 5,000 pesos, we apply the simple interest formula with 5,000 pesos, rate is 0.06 and time is 1/4 to find the amount in the account at the end of the first quarter. So solution goes like this. A is equals to P plus PRT. P times 1 plus RT. 5,000, which is the value of P, times 1 plus 0.06 times 1/4, and it is equal to 5,000 times 1 0.015 is equal to 5,075 pesos. So, 5,075 pesos is the answer. Another type of interest is compound interest, where A equals amount, P equals principal, T equals time, R equals rate per year, and N is the number of times compounded. As you can see, it is different from simple interest because there is N, which is stand for number of times compounded, and the formula for that is A equals P times the value of 1 plus R over N times NT. So, we have an example. For example, if 350 pesos is deposited in an account paying 12% compounded monthly, then how much is the account at the end of 6 years and 6 months? So, the solution is interest is paid 12 times per year. So, it is 12 because it is months. So, in a year, there is 12 months. So, we write 12. So, the account earns 1/2 of 12% or 1% each month for 78 months. It becomes 78 months as we convert 6 years and 6 months into months. So, the solution is A equals P times the value of 1 plus R over N times NT. A equals 350 times 1.01 raised to 78, and A is equals to 760.56. Approximately, rather. The third type of interest formula is the continuous compound formula. If P is the principal or beginning balance, R is the annual percentage rated compounded continuously, T is the time in years, and A is the amount of ending balance, then A is equal to P or E raised to RT. The value of T in the continuous compound formula must be in years. For example, if the time is 1 year and 3 months, then T is equal to 1.25 years. If the time is 3 years and then 145 days then. So, example, T is equals to 3 plus 145 over 365. So, it is 3.3973 years. Example for that is if 350 pesos is deposited in an account paying 12% compounded continuously, then how much is the account after 6 years and 6 months? So, solution is A equals P E raised to RT. In this case, we should use a scientific calculator. It is equal to 350 raised to the value of E times 0.12 times 6.5. So, it is 350p, the value of E, raised to 0.78, and it is equal to approximately 763 pesos and 52 centavos. The second type of function is logarithmic function. Logs and exponentials are inverse function of each other, so let's see what we can tell about graphs of logs based on what we learned about the graphs of exponential. Recall that for functions and their inverses, x raised to 1 and y raised to 1 is trade places. So, anything that was true about x raised to 1 or the domain of a function will be true about y raised to 1 or the range of the inverse function and vice versa. Let's look at the characteristics of graphs of exponentials and then see this tells us about the graphs of the inverse functions such as the logarithmic. Logarithmic functions. Exponential and logarithmic have relationships. For x is greater than 0 and b is greater than 0 and b is not equal to 1, the logarithm of x with base b is defined by the following. Log b, x is equal to y, as verse x is equals to b raised to y. Y log b subscript b raised to x if and only if x is equals to b raised to y. When you convert an exponential to log form, notice that the exponent in exponential becomes what the log is equal to. Just like exponential function, we should also use scientific calculator with calculator keys log or ln. Change base formula for x is greater than 0 for any positive bases a and b. log bx is equals to log ax over log ab. Theorem summary logarithms. Number 1, log b times x and y equals to log b x plus log b y. Number 2, log b times the value of x over y is equals to log b x minus log b y. Number 3, log b x raised to r is equals to r times log b times x. Sample problem of logarithmic equation. Log 3 is equals to 2x plus 5 equals to x equals 2. Log 2, 5x plus 1 minus log 2 times x minus 1 equals 3, so x equals 3. Log 2, x plus 2 plus log 2, x equals 3, or x equals negative 4, or x is equals to 2. As you can notice, the characteristics of graphs of exponential functions where f in terms of x equals a b raised to x, b is greater than 1. And the characteristics about the graph of log functions is f in terms the value of x equals a log b x, where b is greater than 1. Let us graph the exponential function y equals 2 raised to x. When we add the function f in terms of x equals 2 raised to x to this graph, it is evident that the inverse is reflection to the y equals x axis. So, observe the exponential graph and logarithmic graph. Graphs of inverse functions are reflected from the line y equals x. So, the exponential graph, as you can see, the line increases, while the graph of logarithmic graph, the line decreases. So moving on, we are here in the part in which we convert this kind of exponential form. So log 2 is equal to 2x plus 1 equals 3. 2 raised to 3 is equals to 2x plus 1, where 8 is equals to 2x plus 1, 7 equals 2x, 7 halves equals x. So by checking, log 2 times the value of 2 times 7 over 2 plus 1 equals 3. Log 2 times 8 is equals to 3. Therefore, this is true since 2 cubed is equals to 8. To remember about logarithmics, it has product property like log b is equals to mn is equals to log b m plus log b n, and log b times m plus log b n is equals to log b m times n. Example is log 2 times the value of 3 plus log 2 times the value of 5 is equals to log 2 times the value of 15. The quotient property, log b times the value of n, m rather, over n is equals to log b times m minus log b n, and log b times m minus log b times n is equals to log b times the value of m over n. So example for that is log 2 times 21 minus log 2, the value of 7 minus I equals rather log 2, 21 over 7. Next is a power property. X log b m equals log b times m raised to x. And example for that is 2 log 2 times 7 is equals to log 2 7 squared. Equality property. If log b raised to x is equals to log b y, then y equals x is example is if log 4 7x is equals to log 4 28, then 7x is equals to 28. Last is the miscellaneous property, where log b times the value of b is equals to 1. Example, log 5 times the value of 5 is equals to 1. Log b 1 equals 0. Example is log 5 1 is equals to 0. Last is log b raised to x is equals to x, where log b, as an example, log 5 rather 5 squared equals 2. So thank you for listening. That's the end of the discussion of exponential and logarithmic function. I hope you learned something throughout my video discussion, and thank you for listening again. Bye.